On the one hand, there's the calc side of it. Okay, the calc side's really easy. I want to make sure you guys don't lose track of the physics meaning behind it, right? I'm really trying to bridge what you see in calc, what you do in calc, and how that applies to the physics. The calculus lets us determine expressions and values that help quantify what's happening in real life. But don't forget, we're talking about accelerations here, we're talking about velocities, we're talking about how things move, how things speed up, slow down, so on and so forth. Okay, well, let's go right into it. So then the velocity will be the integral of this with respect to time, which is going to be just the integral of a naught dt, which is just at, a naught t, plus some initial velocity, right? That's your plus c. Technically, when you do your plus c, what you're supposed to do is you're supposed to start with plus c, and then you say, okay, well, what if time is equal to 0, but that's equal to 0, and then, you know, your c is equal to v at time equals 0. But we'll just keep going. So the next step is we want the position. So we have this one, right? Here's your v naught plus at. Now if we look for a position, this is the integral of the velocity with respect to time. So I will substitute a naught t plus v naught dt, right? And again, as you get more proficient with taking integrals, it honestly isn't really any different from memorizing your multiplication tables, memorizing derivatives. You kind of just start getting familiar with what integrals are without really having to think about them. So you raise this to a power and divide by that much. This gives you the a naught t squared over 2. And then here's the other term plus integral of that, v naught t, and then plus x naught, right? So pretty straightforward, and honestly, in how to derive the kinematic equations. Okay. So hopefully now you can see why we said it has to be constant acceleration to use these, because these you only get these if you have constant acceleration. If you don't have constant acceleration, well, we got something like this, right? It was a little different. You had like a cubed thing, and it depended on what the function was. Right? There are a lot of different kinds of functions for your acceleration. I'll tell you this: a lot of times, we don't generally have functions for acceleration. What we do have is we have functions for a force, and the force leads to an acceleration. And so a lot of times we say there's some sort of forcing function. So is it a spring? Is it gravity? Is it drag? Is it magnetic or a magnetic force, electromagnetic force? All these different forces, simply by dividing by the mass, you get the acceleration due to those forces. And then you end up, okay, now if you want to know the velocity with respect to time, position with respect to time, you have to integrate. And what you'll find is that the integral is not always very easy. Right? That's the problem. That's what makes the physics hard, is when you have a complex integral. So let's take a look at one, for example. This was actually in chapter 14. Actually, I guess before we get to that, I think it's worth revisiting all the different equations that you guys had in your equation sheet. And again, look at how for a lot of these equations, if there is some sort of derivative going on, there is also meaning in its integral. Okay? So, for example, if you look at Newton's second law, we always say F equals ma, but and it's kind of written like right here. But honestly, it's more meaningful to look at it in terms of a change in momentum. If F is equal to a change in momentum over change in time, and I'm not writing it as a vector. Technically, I should, but let's just say it's momentum in the x direction only, right? And force in the x direction only. So if I have something pushing in the x direction only, and so I mean we can specify that, and that leads to some sort of momentum change in the x direction only. then just like with acceleration, we can do the flip side of that. We can write a meaningful integral where if you kind of start noticing the way we write it out, if a is equal to like a dv dt, okay, technically, I'm not multiplying both sides by dt just to bring it over. But you kind of have that same effect. If f in the x, a force in the x direction leads to a change in the momentum in the x direction with respect to time, then that force in the x direction over a infinitesimal amount of time will lead to a net change in momentum, infinitesimal change in momentum. Okay. When I write it like this, there are, this is not generalizable. You have to be very careful about writing it like this. Like if you start getting into vectors, if you start getting into, well, yeah, I honestly am not very clear or don't remember exactly the rules around being able to write it in differential form like this, like a force over an infinitesimal time is equal to some infinitesimal change in momentum. A lot of times you can write it like this, but I just want to point out it's not like you're just multiplying both sides by dt. It's more like if there is some function p and its rate of change with respect to time is f, then you're really kind of looking at the area of that little bit of space. And then we're just adding it all up. Okay, we're adding it all up. That's really where this is coming from. So that if you add up this force over a bunch of time, you lead to a net change in momentum, right? And you can do this for work as well. See, we said if you take, what was it? Well, actually, we had it like this, right? Some force in the x over some positional change in the x equals to work. Okay, and again, I'm using x as like a special case. Okay, a special case, let's just keep it one-dimensional. Everything is in x direction only. When we generalize it, we got to use dot products and stuff. I don't want to worry about that. I want you to focus on the integral part. Okay, how do we write this, the complement of this? Complement is not maybe the best word, right? How do I reverse this? If fx dx equals to work, then what does this equal to with respect to work? How do I write an expression for this? What would that be? dw dx, that's it. So in other words, if you apply a force over a short distance leads to an incremental amount of work, then the rate at which work is done over a distance is equal to the force that's applied, right? There's this, again, two representations for the same phenomenon. And they kind of have this, well, I guess they don't really say this, that one in your equation sheet. They don't really talk about, yeah, they have this part, but they don't really do the derivative side. But sometimes it's good to know. It's good to know. Also, this comes up too, since if you have a conservative force, if you have some change in potential energy, which is a function of position, and that was equal to the negative, sorry, it was like this, right? We've been talking about this a little bit. Work done leads to a negative change in potential energy. Then you can actually substitute that in, and you can say this is like a negative du dx. So in other words, if a force leads to an incremental change of work over a little bit of space, then by necessity, it also can lead to a change of potential energy over that little bit of space too. I think we had talked about this way back. We kind of talked about equal potential lines and all that kind of stuff. We'll come back to that. But it's very useful. Other functions. Okay, there's one last one that kind of came up. We said the power is equal to like dw dt. Okay, so this is work over space. This is work over time. They're different. So as you do work over time, that is related to your power. So then, again, conversely, if you have a certain amount of power applied over a certain amount of time, that should also lead to the amount of work done. Right? And a lot of times the kind of problems that you'll see will be something like, okay, the power, you have constant power, 60-watt light bulb, you let a 60-watt light bulb run for 10 seconds, how much energy is transferred, how much energy is used, right? It just ends up being the product. It becomes easy. But sometimes your power is not constant. Sometimes your power is changing. Sometimes it's changing with respect to time. So if you want to know the net amount of work, energy consumed or transferred, you would actually have to integrate that. Okay, that may come up. Okay. Honestly, I think that's about it. In terms of all the different physics properties that are related to the rate of something else, that's it for now. Okay, when we get to electricity and magnetism, there's a lot more of these. So for now, we'll leave it at that. Okay. So, I mean, I guess even though they're different functions, they're like, you know, you're talking about force and power and gravitational potential energy, they're still integrals. They act like all other integrals. They have some limits of integration. Most of the time, the function they'll give you will be some sort of polynomial function. You know, you just treat it like whatever function you would see in calc. Okay? So you don't have to throw all your calc out the window. You want to use it. Okay. Let's look at a couple special cases, okay? Particularly unusual, or not unusual, but challenging cases. In chapter 14, you guys were supposed to look at how springs, a mass on a spring behaves, right? That was one of the things that came up. This spring might have some spring constant K. Excuse me. And let's say this is at 0 position and you stretch it out. You stretch it out some position x, right? And then you let it go. At any moment, the force on the spring, we'll say it's an ideal spring. So it'll follow Hooke's law. We'll say it's negative kx because the force will always be in the opposite direction of the stretch. So if it stretches to the right, the force is to the left. If it compresses to the left, the force is to the right. Okay. So the question is, what a lot of times when we end up doing this calculus stuff is, I want to know what is the position. Whoops. What is the position at any time t, right? What is the function that describes the position of this block? Well, to solve this, we need to use Newton's law. The sum of the forces on this object is just the negative kx, and that is equal to ma. Right? But what? Oh, gosh, drink some water here. So what is A? A, I want to try and get A in terms of x. This will be like a m d squared x dt squared. Right? So if I look at my acceleration, I can write it like this: d squared x dt squared is equal to negative k over m x. Right, so my acceleration is equal to this. So remember how I was saying you want to try and get your function in terms of the thing that you're taking derivatives with respect to. This is a second order derivative with respect to time, but my function is a function of position, and my position is a function of time. We don't know what that function is. If we knew what that function was, then we could integrate it and we could do all that stuff and it'd be fine. But we don't. So there's a couple ways we can write this. We can write it like this, or we can write it like this. Okay, you can put it on the same side, or you can keep them on opposite sides. However you want to say it, the rate of change of your function is related to the function itself. That's not always the case. Okay. This is what we call a differential equation. It's a differential equation because it's an equation that relates a function with its derivative, or second order derivative, or whatever it is. Okay. It's going to be an interesting video. So, you, on the AP exam, are not expected to solve differential equations. They will not throw a totally random one out there for you to solve, but you do need to know how to set them up. You need to be able to get to this point. Kind of like on the test I just gave you guys with electrostatics, with trying to create the integral, you need to be able to create this, this differential equation. Okay. Now, what makes it a differential equation, again, I could have written it like ma plus kx equals to 0. That's not quite the right way to write it. The reason why is because this makes it seem like a and x are not related, that they're not connected. By writing my acceleration as the second order derivative of position with respect to time, what I'm saying is that this function is appearing twice. It's appearing here, and it's appearing as its second order derivative. That's what makes it a differential equation, and you need to be able to do that. Okay. Most of the time, what will end up happening is you will just use Newton's second law, and then you will just substitute this d squared x over dt squared for a. That's most of the time, that's what's going to turn it into a differential equation. And then you get to here and you're like, okay, I'm done. There's a couple special or specific differential equations that you need to know the solutions for. And when you take differential equations in college or PCC or wherever it is, most of these differential equations, some guy some time ago figured out a solution for it, and you just memorize them. Okay. A lot of them have, like, you kind of just guess at a solution until you find something that works, and then you document it, and then it's like, oh, you researched it, and now everyone knows. A lot of them are really hard to just figure out intuitively, right? Kind of like the different proofs of, like, I don't know if you want to use something simple like Pythagorean theorem or something like that. There's all these proofs that someone figured out some time ago, and now we just, like, know them. This is one of those, spring. Let's take a look at how that solution works out. So I'm going to use this one. I want you guys to look at this one. What I want you to be able to do when you look at this, and I'm trying to get you guys to learn, is try to understand what it's saying. It's saying that the second order derivative of this function is equal similarly to the original function itself. So what function do you know of where the function looks very similar to its second order derivative? EX. What else? 0. What else? There's one other function whose second order derivative is cosine and sine, right? Right? Because if you take the first derivative of cosine, it becomes sine, but then you take it again and it comes back to cosine. But you do get, yeah, you get negatives. You get a coefficient, but you can always change that because usually you have maybe some sort of sine omega x plus phi or something like that. You can choose something in here such that when it comes out, it can cancel that all out. So here's the question: of these three functions, which of them most likely describes the position of this spring with respect to time? When you take a spring and you let it go, what happens? It goes like this. So most likely it's some sort of sinusoidal function, right? Although these other functions work, you want to pick one that makes sense. That's the physics part. Most likely it's one of those. Oops, one of those. So let's give it a shot. In general, if x is a function of time, looks like this, some sort of amplitude. Well, how do we choose sine or cosine? Well, if we're trying to describe a scenario where we pull it out and at time equals 0 we let go and it oscillates back and forth, which of these better represents the position when at the initial time you let go it's pulled out? Which of these two functions at time equals 0 or x equals 0 usually start at its maximum? Cosine, right? Sine starts at 0, cosine starts at maximum. So will you go with cosine? In pre-calc, you should have studied sinusoidal functions. There's some sort of frequency and phase shift. Okay, so we'll use the general form of a sinusoidal function. Looks something like this, right? So this is kind of one way to solve differential equations. You guess at a function, and you just plug it in and see if it works. It's at least, I'll put it this way, as far as I studied, okay, I think when you get to more advanced methods, you talk about Laplace transforms, there's other ways to be able to solve differential equations. This is one way. This is one way to do it. Okay, so let's plug it in. So what is the first order derivative? You'll have omega a, a negative omega a, sine omega t plus phi. Right? That's the first derivative. Second order derivative will be a negative omega squared. You guys understand where this omega is coming from, right? What rule is that? Chain rule. Okay, chain rule, right? Derivative outside times the derivative inside. That's where the omega is coming from. A cosine omega t plus phi. So we can substitute. I'm going to take this guy, put it in here. On the right-hand side, I have this negative k over m times x. So this is a cosine omega t plus phi. So, in order for this equality to be true, okay, they both have the cosine omega t plus phi. They both have the a. So for this equality to be true, omega must equal the square root of k over m. So if omega equals the square root of k over m, then this equation will predict the position for for all time. Or in other words, x as a function of time is equal to a cosine square root of k over m t plus phi. Okay. And the plus phi really just depends on whether you're counting at time equals 0 where it's at, right? This is just a phase shift. So you may have a situation where like the spring is pulled out, you let it go, and then you like start counting time a little bit later, right? But it doesn't really matter. Okay. So this is just an example of a situation where you can't just integrate you can't just use integrals to solve your calculus problem. Okay, this is another kind of calculus problem that you may run into. Again, you won't have to do this. You won't have to do something like this, guessing at a function for a unusual function. There are very special cases that we study in physics that you're meant to know this solution ahead of time. Right? It's in your equation sheet. It's this one. It's your job to know what this represents, though. This is talking about. There's nothing in here that says this is for a spring. Actually, this is a generalized description of simple harmonic motion. There are actually a couple other scenarios or physical situations that behave like this. If you've read through chapter 14, masses on springs behave like this. You'll notice that they use omega instead of actually substituting the square root of k over m, because for different situations your frequency will depend on other things. So pendulums also kind of have this sinusoidal simple harmonic motion. And you'll notice that in the equation sheet they don't give you omega, they give you the period, but your period is related to omega. So in a pendulum, it's dependent on the gravity and the length, whereas for a spring, it's dependent on the mass and the spring constant, right? Okay. So yeah, there's other things that go with this, but this is kind of an archetypical behavior, simple harmonic motion. Okay. Questions on, I know we weren't originally studying simple harmonic motion or springs or anything like that, but again, in the context of, what kind of calculus you're expected to see and know, this is part of it. Okay. So I want to give you guys a chance to kind of, again, practice this calculus stuff a little more. So